next speaker is Trung Lam, who's a research assistant in the Department of Cardiology here at the Health Science Center. And he'll be talking to us today about the reversal of intramuscular lipid accumulation through the lipophagy pathway.
How's everyone doing? Everyone's tired by now.
We're good.
I looked through the whole program. I'm the one non-doctor, so I guess they save the best for last. But don't be too hard on me.
We won't.
So first of all, I'd like to thank the organizers for giving me the opportunity to present my project at this year's symposium. And today I'm going to share my project on the reversal of intramuscular lipid accumulation through a novel lipophagy pathway, which I've been doing in these past few years in the Tagmar lab. So first, my hypothesis is that autophagy is responsible for driving the reversal or the clearance of intramuscular lipid accumulation and protects the myocyte from skeletal muscle lipid-induced cell death or cellular dysfunction or lipotoxicity. And the initial clinical observation that led us to arrive at this hypothesis is we noticed after bariatric surgery at the time of baseline to 9 months, we see a dramatic decrease in the amount of triglyceride deposition in these muscle biopsy samples. So as you can see, these are overall stains, and you can see at the time of surgery up to 9 months, you can see almost a complete removal or disappearance of these fats. So much is known clinically, but what is really happening at the molecular level? So that really begs the question of what processes are important for metabolic remodeling of the cell. And of course, at the symposium, the process that we've been talking about all day long is important for remodeling of the cell. But since this is a autophagy crowd, I just want to point out that some of the main triggers are starvation, nutrient deprivation, oxidative stress. And for me, I want to focus specifically on metabolic stress, in particular chronic lipid overload, as you've seen in the bariatric surgery patients or in the obese patients. Also, I want to bring your attention, I'm going to look at two specific molecules that we've been talking about throughout the day, which is LC3 and Q62. And LC3 I'll use, LC3 is it's phospholipidated with phosphatidylethanolamine as an indicator of elongation of the autophagic vesicle, whereas Q62 is an adaptive protein, which is degraded to indicate completion of autophagic pathway. So generally speaking, you've heard a lot of different excellent speakers talk about how autophagy is beneficial and also maybe detrimental. But for the most part, we see that if we upregulate the autophagic pathway, we get a positive response and the cell's ability to resist stress and survive longer. Whereas if you suppress autophagy, it can lead to detrimental effects such as muscle damage and clot disease. So when we were first exploring the association of autophagy and lipids, we wanted to see what was available in the literature. And the first landmark paper that showed an association between autophagy and lipid metabolism was in Nature in 2009 by Sang and Saja. And what you can see, and I know this is a crowded slide, but just some of the key observations that they had made is that if you look with increasing oleate concentration in either the knockdown, the pharmacological inhibition of PI3K class 3, which is important for the initiation of autophagy, or the ATG5 knockout, you can see that in the ones treated with the suppression of autophagy, you see an increase in triglycerides compared to their respective controls. Here you see Bodipi, which is very similar to, Olredo, but it stands for neutral lipids in immunofluorescence, and you can see that with 3-methyladenine, there's an increase in them with the knockdown. Again, you see a more dramatic increase in these lipid droplets. And here in the electron micrographs, what you can immediately appreciate is in these fully vehicle treated, you have some increase in lipid deposition, and you see a much more remarkable increase with the knockdown of TG5. So this goes to show that if you knock down or impair autophagy, there is an impairment in the ability for the cell, in this case specifically hepatocytes in the mice, to break down lipids. So then we went on to see, has it been explored whether autophagy or lipophagy is used in skeletal muscle, and there was a plethora of papers after that landmark paper in Nature in 2009, but no one's really looked at it in the skeletal muscle, especially in the context of obesity or chronic lipid overload. So the current thinking for how lipophagy works is all the ATG molecules are recruited to the lipid droplet and associate with paralipins. They sequester a portion of the lipid droplet, form an autophagosome, fuses with the lysosome. The lysosome then transports the fat to the mitochondria for beta oxidation and subsequent ATP production, and this process is called lipophagy. What I'd like to try to convince you today is there's actually another arm of this pathway that branches off of this canonical pathway that is triggered whenever there's chronic lipid overload or impaired lysosomal fusion. So just to review what we already know, bariatric surgery is an end-stage treatment for obesity. And from that, we published a paper looking where we made the observation that there was a restoration of derangements in muscle metabolism. And we hypothesized that what is driving this at the molecular level is lipophagy. So I think there are two important objectives that come from this hypothesis. One is the obvious one, like we had seen in the Nature paper, to look at the impact or relationship between autophagy on lipid accumulation in cultured myocytes. But I think what is also important that a lot of people don't really look at was the effect, the flip side was the effect of lipids on autophagy itself, because it has been shown that lipids itself can disrupt the autophagic pathway, namely at the fusion of the lysosome and the autophagosome. So in order to metabolically manipulate and pharmacologically manipulate muscles, we decided to use L6 myocyte because they're very similar to human muscle cells. First, they start off as this progenitor-form myoblasts. They then differentiate into myocytes and then fuse into myotubes. Very similar to the muscle cells that you had seen in the bariatric surgery patients on the first slide. So how did we modulate autophagy? Well, we did so pharmacologically. We used rapamycin. Everyone knows it's a well-known inhibitor of mTOR, which inhibits autophagy, thereby it activates the autophagic pathway. Vancomycin is a vascular hydrogen ATPase inhibitor, so it blocks the lysosome autophagosome step. And one would imagine, as I'm sure a lot of you guys know, that with this step, there's a huge accumulation of autophagic vacuoles. So in the experimental design, my first set, I have a 6-day protocol where for 4 days. Can you guys hear me if I step away? For 6 days, I treat, for 4 days, I treat with fat. I treat with 1 of 3 different fatty acid treatments, either the control, which is albumin fatty acid free treatment, 0.5 oleate palmitate, which is a physiological medium, and 1 millimole oleate palmitate, which simulates a diabetic or hyperlipidemic medium. 24 hours before I extract the myocytes for analysis, I treat with either the activator autophagy, rapamycin, or vancomycin. And this is just to simulate, like we had seen in the obese patients, does autophagy have an effect on the on lipid metabolism? And here you can see LC3 and PC2, and these indicate very nicely autophagic flux. As you see with the rapamycin treatment, there is an increase in LC32, and there is a decrease in the degradation of P62. What's also important to notice is that in the increase in fat, you see there's a decrease in the phospholipidation of LC3, which seems to suggest that maybe there's a decrease in autophagy, but it's also important to look and notice that there's a significant decrease in P62 still. So I think it's important to kind of look at the whole picture, LC32 and P62, and if you notice that with increasing fat, you do still see increased autophagic flux. Maybe not as much as here, but with the fat, there's still flux happening. So here, this is just immunofluorescence to confirm the flux. In control, you have basal levels of autophagy with rapamycin. You have a slight increase for upregulation of autophagy. And these are all 50 LC3 puncta. And vancomycin, you get an even further increase, which is marked by the inability for the cell to degrade the autophagosome because the fusion step has been inhibited. So what I think is really remarkable as part of the lipotoxicity story, we wanted to see if the different autophagic drug or the different pharmacologic modulators of autophagy had an effect on triglyceride accumulation. And what you can immediately appreciate is, which is not surprising, with increasing fats you get an increase in triglycerides. But within each treatment group, you see with the rapamycin there's a dramatic decrease in the amount of triglycerides, whereas with vancomycin there's a dramatic increase. You see the same here with the 1 millimolar treatment. And to see if this was leading to cell dysfunction or lipoapoptosis, we looked at cleaved caspase-3 levels on Western blot. And sure enough, we saw that with rapamycin, it seems to sort of protect against lipid-induced cell death, as evidenced here by decreased cleaved caspase-3. And with vancomycin, you see it promotes more apoptosis, as evidenced by this good caspase 3 here. So in summary this is actually my first part. Rapamycin increases autophagy by, as you can see, as evidenced by increase in LCP2, decrease in PCX2 markers. Rapamycin reduces lipid accumulation, seems to have a protective effect on the cell. Vancomycin decreases autophagy, and you would see an increase in both LCP2 and PCX2. This leads to sort of a lipotoxic effect. And like I sort of had alluded to earlier, fat alone is not killing cells, but it's also the impairment of autophagy in conjunction with fat that's leading to this lipotoxic effect. So the last set of experiments I'm going to present today, what I want to do is I want to extend the protocol to 8 days and see if a longer incubation time for the fat and longer incubation time for the drugs will still preserve the autophagic flux, and if there were any differences in the lipotoxic effect. And here I removed the 0.5 millimolar because I just want to see did fat have any sort of effect at all, high fat or no fat. And here I also added 2 drugs. I added a combination treatment of rapamycin and vancomycin, and that's actually one of the ways that people use to determine flux, because as you can imagine, when you accelerate the process upstream and inhibit the process downstream, you get an increase in the amount of LC3 and P62. So this here just shows the efficacy at 48 hours looking at LC3 P62 ratio, and we see that actually at the 48-hour treatment that I just used for the drugs, there's actually a much more robust response in terms of autophagic flux. Here, as I mentioned before, with LC3, this is what we would expect. We see an increase in rapamycin in both fatty acid groups, see an increase in vancomycin, and then we see the combination treatment yielding either the same levels of protein or slightly higher. But what's really interesting is, if I can direct your attention to the 1 millimolar treatment here, is that in the P62 levels, we have what's expected with rapamycin, increased degradation. We have decreased degradation here, meaning increased levels of P62. But with the combination treatment, we get a dramatic decrease, almost as if vancomycin has no effect. So this led me to start thinking, well, maybe there's some other process by which P62 is being degraded, if it's not being degraded by a lysosomal pathway, because vancomycin is inhibiting that pathway. So then, just to further the lipotoxicity story, I wanted to see what was happening in terms of cell death. And here you see also that there's a significant decrease in the amount of cell death with this combination treatment. Here, this is immunofluorescence, just confirming the same thing. You see that 1 millimolar, there's some cell death, there's decreased cell death with RAPA, and you see that most of the cells here are already dead, and the ones that are left have a huge amount of cleaved caspase 3, that's marked by the green here. So the next set of slides, I'm going to look at overall stains. If you look at BSA, this is not surprising. There's no sort of lipid deposition, but what you can appreciate is that in the vancomycin, these guys already look really sick, and a lot of them are dying, whereas vancomycin seems to be a little bit healthier compared to the vancomycin alone. And you can see this even better with the 1 millimolar treatment. With control, you see dramatic increase in the amount of triglycerides. Rapamycin, there's a dramatic decrease. Vancomycin, there's a much more remarkable increase in the triglycerides. And here, surprisingly, in the vancomycin, you see that the levels of the triglyceride accumulation is actually less than the control of vancomycin, almost something in between these two. So again, looking at the P62 levels, the cleaved caspase 3 and the vancomycin triglyceride accumulation seems to suggest that there may be an alternative pathway by which P62 is being degraded or triglycerides are being processed. So is there a new pathway? So I thought, well, since P62 levels are decreasing, maybe P62 is responsible for trafficking the lipids. And what I have done initially is I looked for, in immunofluorescence, co-localization of P62 and VODIPI. What you see real nicely is P62 here is labeled red, and VODIPI is, like I said, an oil stain but full of lipids. And you see sort of whenever they associate or co-localize, you have a Bayesian effect. You see real nicely, almost all these cells here are brown. So we therefore propose that lipid droplets not only undergo the canonical pathway, but what happens is when there's an impairment of some sort of defect in the lysosomal fusion step, or this chronic lipid overload, P62 then takes over and mediates or causes or initiates the lipid droplets to enter an alternative P62 mediated lipolysis pathway. And we're still trying to figure out if there's an increase in lipolysis, intracellular lipases, and what is the ultimate fate of these cells? Are they going to the mitochondria for beta oxidation, and there's been evidence in literature to suggest that maybe lipids are actually being exported outside the cell as well. So just to quickly summarize, the combination treatment yielded some unexpected effects. We saw lower levels of intracellular lipid accumulation, lower p62 protein levels despite inhibition by lysozyme fusion in the combination treatment, and lower levels of cell death. We saw that complete caspase 3 indicates the increase in cell death with the vancomycin treatment, and then p62 you see very nicely co-localized with the lipid droplet in these treatments. So conclusions that with vancomycin treatment, you have an increase in triglycerides and inhibition of autophagy. Rapamycin, which you get a very potent activation of autophagy and decreased triglyceride accumulation. And what does that mean for cell death? In terms of cell death, impaired autophagy by rapamycin leads to increased lipotoxicity, and rapamycin seems to sort of protect these cells from that lipotoxic effect. And what's most interesting is it seems like there's an alternative lipid degradation pathway which may be activated with this combination treatment. And rapamycin may be essential in reversing lipid metabolism defects caused by some sort of impairment in that fusion step, leading on to some sort of P16-mediated glycolysis. So this is what I'm currently working on in the lab. Is it really lipotoxicity? And I think it's also important to look at the other metabolic arm. What is happening to glucose uptake and insulin sensitivity? And if this is a P62-mediated pathway, what's happening in terms of the fat? Is it going through beta oxidation or is it being exported? And we can look at, there's this new adipose triglyceride lipase inhibitor called aclastatin, very creative name, to look at rates of beta oxidation with respect to the different treatment conditions. Then we want to look at pulse chase just to see if over time radiolabeled fat is being secreted into the medium. Also lipase activity, look at intracellular lipase, and ultimately does the same occur in vivo. And last but not least, I'd like to thank the Timer Lab for putting up with me these last few years, and thank you for your attention. I'd be happy to take questions. Thank you.
So have you been, I mean, right now, you've got a correlation with P62. Have you been able to functionally show that if you knock it down, that it all affects it yet?
Yeah, I mean, that's an obvious next step. Right. We haven't done it yet. So, yeah. Okay, thank you.
Thank you, Tron. So just to close out the session, Dr. Tegmeyer will come up and say a few remarks.
Thank you all for remaining to the very end. This has been a terrific day. And I think we have every reason to thank the organizers, Jack and Andre, and also Diane and Stephen, who can be here, for bringing us together and for selecting a wonderful group of speakers. We know that there is an incredible wealth of expertise and intense interest in this particular topic here in the Texas Medical Center and in many, many, many other laboratories around the world. I think we've tried to do justice to the very diverse field of autophagy, and the things that I liked in particular, the dynamic nature, and I think the originality of the ideas. And believe it or not, until just the coffee break here, I thought I would give a rundown on what I liked in particular about today's talks. And I looked at, I took notes, I took 45 pages of notes. And I felt overwhelmed by this. And I like to share with you, number one, our profound gratitude with all the speakers. And number two, the recognition of the originality of the ideas, the diversity, and the tight logic. I think each and every presentation was outstanding in its own. And at my age, you feel, even though, the NIH continues to support us in the lab, and we have a rather dynamic group of people interested in cardiac metabolism in particular, protein turnover. My age, I feel sometimes when you hear a good presentation, I feel like I'm at the gates of heaven. And this today was certainly one of those days where I personally felt richly rewarded for the work that I find so incredibly fascinating, and that is the biology of the cell and the dynamics of the cell. So some of you might know I've been the last graduate student of Hans Krebs, and his picture is here. Oh, no, you don't have to advance this. His picture is here, and I also have 3 words of his own handwriting, and yeah, okay. His own handwriting when I had handed him the first draft of my thesis, and he wrote very perceptively, main conclusion missing. So what's the main conclusion of our symposium today? Well, the main conclusion of our symposium, I would say, is that there is no life without autophagy. And being a disciple of Hans Krebs, I like to see autophagy as yet another example of the cyclic processes in the cell. The cell operates most efficiently by cycling and recycling its constituents. And autophagy is only one of many examples of how the cell operates in such an efficient way of reinventing itself, self-renewing itself, and also in the process of energy transfer. We know from the Krebs cycle, and again, I'd like to pay homage to this very modest man. He was a physician and never considered himself a great biochemist, but he was the one who first had the idea of metabolic pathways occurring in cycles, with the urea cycle in 1932 and the discovery of the citric acid cycle in 1937, which both of which have proven their validity through now nearly a century. So there's no life without autophagy, and all of us were standing on, of course, the shoulders of giants, and some of these giants have lived thousands of years ago already. The first one, I'll be very brief. First one I'd like to refer to as Heraclitus, lived in Ephesus in Asia Minor, it's now Turkey, who looking at the shore, looking at the water, looking at the river, he came to the profound conclusion that in nature, in life, everything is in flux, all is in flux. And that was, I think, the first formulation of the biological concept that includes autophagy. And then, much later, at the beginning of the last century, or mid-last century,